Very important concept, driving potential and thermal network. Driving potential and thermal network. So this concept is very important in the sense that you need knowledge of this concept to solve any problem in the heat transfer. So please pay your attention fully. Let's see the Fourier's law once again. The rate of heat transfer in any given direction is minus Ka dt by dx. Of course, to make it simple, we are writing this as Q. Otherwise, strictly speaking, when we are talking about temperature gradient in x direction, this is right. It is flowing in the x direction. But we are not writing it every time. Right? Just because by default you can relate to it. So now this is in differential form. So when there is a small change in temperature dt over a distance dx, small distance through which the heat is transferred. Now in integral form, this equation has become qx or q K A T1 minus T2 by L. When dx is integrated over the entire thickness being considered as L, this becomes L. Integral dt is T between the limits 1 and 2, it becomes T2 minus T1, and minus of T2 minus T1 is T1 minus T2. And this can be rearranged as T1 minus T2 divided by L by K. So this T1 minus T2 represents the difference in temperature between any two given points. It need not be just 1 and 2. It can be 3 and 4. It can be 1 and 5. There may be many different points. Whichever the points you consider, the difference between these 2 points, temperature difference between these 2 points, divided by L by K. So now this equation has become, simply if you take this as Q is equal to delta T by L by Ka. See, why at all this heat transfer taking place, how this heat is flowing? Because of temperature difference. Temperature difference is the cause. Heat transfer is the effect. If there is no temperature difference, will there be any heat transfer? No. So that means delta T is the fuel for moving this. And what is this? This is the resistance. So imagine you are riding a vehicle. So your fuel is the input energy for running the vehicle. But that vehicle has to overcome some resistance, say in the form of friction between the road surface and the vehicle or tires, and the friction or drag that is offered by the wind, right, which is opposing the motion of the vehicle. All these factors represents the resistance to the motion of the vehicle. Similarly, for any movement, right, there will be some resistance. Imagine there is no resistance at all that is offered by the road, right? Just like, perfect, smooth, ultra smooth, where, we do skating. We all do skating, right? So, do you need to apply big effort there once initial motion is given? No. So, without effort you are moving. So, why? There is no friction, there is no resistance. So, the denominator is 0. This concept is applicable for everything. Now, even you can compare this with Ohm's law. What is Ohm's law? Current is equal to delta V by R. What is R here? Electrical resistance. So what is delta V? Voltage difference. So voltage difference is the cause, current or conduction of electricity is the effect. If there is no voltage difference, there is no electricity that is passing through any conductor. See, you can demonstrate this experience practically. We all know that if we touch electrical transmission lines, right, we will die. Our effect is more severe. But at the same time, we also see that birds are standing on it comfortably, sitting on it. We see it, right? Small birds sitting on them, electric lines. But are they dying? They are not. Why? What's the reason? Right? So there are the lines, there are electricity lines, and the bird is sitting here like this, right? Nothing is happening to it. The reason is, see, there is a potential here. Let's say this is a 230 watts line. And the moment it touches, it may try to go there, but where it should go? There must be other end of it, right? There is nothing like that. But the same bird, if it sits here during a rainy day, when it's raining, right? Then that rain droplets will connect this bird to the earth surface. So this is the earth surface, whereas this is the transmission line. Earth has zero potential, voltage is zero. So now what happens? This is connected to the earth. That means this rain flow or water flow, water stream becomes the conductor. This becomes the conductor. So now there is a voltage difference of 230 minus 0, that is 230. So therefore through this, through the body of the bird and this water stream, the current passes. So therefore this body cannot withstand that and it will die. And we can talk about it, in many different ways. See, suppose you are here, a person standing here without touching earth. Suppose if he is touching this wire, nothing will happen. But the moment he touches the surface, he will collapse, because now this body has become the conductor. Our human body has become the conductor, and electricity passes through you, and we cannot, withstand that. We cannot sustain it. We cannot bear that effect, right? So you often hear, as a precautionary measure, whenever some electricity repair works or erection work is going on, people are advised to use slippers, strong slippers. Reason, they are insulators. Slipper is made up of a material which is highly insulating in nature. So therefore, you are avoiding contact with the surface. So again, right, there is no connection and hence electricity cannot flow through it. So therefore, there is no severity. Now, as such, it's not perfect insulator. That's the reason why there may be slight shock, because still small amount of current is passing through. Our body can withstand small amount, but not bigger thing. See, whenever we accidentally, put our fingers in sockets, we experience that, but it's not very severe that it will harm our body. But if you touch higher transmission lines, you will collapse there immediately, because this is going up, right? So similarly, same is the case here. Delta T is the potential difference, and this is the flow, and this is the thermal resistance of air. So this can be written as delta T divided by RTH. There, that is electrical resistance. Here this is thermal resistance. Now imagine a plain wall, right, like this. A plain wall of thickness L, right? thermal conductivity K. One side of the wall is at a temperature say T1, other side is at a temperature of say T2. Then T1 is greater than T2, right? So now this is the equation. You can represent it in the form of a thermal network. See, there is T1, right? And between T1 and T2, there is resistance. This resistance is thermal resistance. In this case, this is L by K, and your heat is flowing in this direction, say Q, the X direction. So this is thermal network diagram, and this concept is applicable, right? For see here, this is conductive resistance. Similarly, if it is convection, we will get convective resistance. Radiation, similar resistance, right? Just like we have electrical resistance there. So now the equation becomes rate of heat transfer is equal to temperature difference divided by resistance. Right? In this case, it is conductive resistance. Right? Resistance offered to the conduction heat transfer. So is L by K. Now if it is convective heat transfer, apply the same concept. So convection, as you know, is governed by Newton's law, is H A Ts minus T infinity. Ts being the temperature of the surface or solid body over which the fluid is flowing, and T infinity is the temperature of the fluid. I said earlier why we are writing infinity here, because in general, the fluid could be atmospheric air, which is huge in quantity. So that's the reflection of this. So this can be written as Ts minus T infinity by 1 by HA. So now this also will become delta T. Here delta T is the temperature difference between the solid body and the fluid. Here delta T is the temperature difference between 2 points of the same solid body, right? Or maybe different bodies also. Divided by, again this becomes convective resistance. This is R convective. So convective resistance between solid and a fluid flowing over it is 1 by HA. Remember, A here is area perpendicular to the direction of heat flow, whereas A here is area of the surface over which the fluid is flowing. There is a difference in meaning. In some cases, both may be same, right? Depending on the configuration or geometry of the object, but their meanings are completely different. Okay. Ts, T infinity, and this is our convective resistance, which is 1 by HA, and the heat is flowing in this direction, positive x direction, which is separating two fluids. On one side, hot fluid, and other side, cold fluid. Right? Just imagine this room is air conditioned in hot summer condition, right? So now inside it's cold, and outside this is hot, right? So the meaning of inside and outside is this. Suppose if you take this wall, the air, this side of the surface is called inside surface and the other outside, right? So the wall is separating two fluids. They can be the same or different. Now, what are the different modes of heat transfer that are involved here? See, there is one fluid and adjoining surface, and there is another fluid and adjoining surface. So therefore there will be, you may please put off this fan, is this. What is the mode of heat transfer between this fluid and the solid surface here? Fluid and adjoining surface. What is the mode of heat transfer? Convection. Now, within the plane wall, from one side of the wall to the other side of wall. See, now the potential difference for heat transfer is, please remember, the temperature difference between hot and cold fluids. So heat is flowing in the x direction as shown here. So therefore the temperature is dropping in the direction of x, right? So now, because of temperature difference within the wall, the heat transfer here is by conduction, and thereafter between this surface and the surrounding fluid, which is cold here, again convection. So how many resistances this heat transfer has to overcome or come across? There are 3 resistances. So now, how do we put all these 3 resistances in a single thermal network is another important thing that you should understand. So let me do it for you. There is one important point that you all need to know. In fact, we covered it earlier, but then for your quick reference. See, this is one of the terms that we had in the intermediate steps while deriving the heat conduction equation in 3-dimensional heat transfer, general heat conduction. We derived final equation dou square T by dou x square plus dou square T by dou x square, right? That equation is there. In between, right, you go back and you refer to your notebook. You could see, right, this is in the form of, in this form. Dou by dou x of k into dou t by dou x plus dou by dou y of k into dou t by dou y. That's how we have got the equation. From that, we move further, assuming, right, k as constant. Then k was taken out of this differentiation, and this has become d square t by dx square. But now, if you stop at this and see is equal to 0 is for the simple version of, can't you switch off this fan? For one-dimensional steady state heat transfer without any internal heat generation, this is the equation. Now tell me, what is this k into dt by dx? When q is equal, right, minus k dt by dx. Of course, you know the meaning of minus, right? So this q by a is minus k dt by dx. So this is q double prime, which is heat flux, is equal. If that minus is absorbed, this is k into dt. If you want to be very specific, right, you can write this as qx. Even if I don't write x, you should understand it. It is in x direction by seeing the temperature gradient, right? So now, what is the meaning of this? D by dx of k into dt by dx is equal to 0, right? Where it is coming from? We know the general conduction equation in one-dimensional steady state heat transfer is d square t by dx square is equal to 0, right? I said this has come with an assumption that k is constant. So this can be written as d by dx of dt by dx. Now if k is brought inside, right, we don't know whether it is constant or not, this is the equation. So now this is d by dx of, so this term represents heat flux, right? So when is this possible? Only when this q double prime is Chepan. When this is possible, when d by dx of something can be 0, when this something is constant, right? Then this must be constant. If it is a variable, you have to differentiate it with respect to x. But now the meaning of this equation is that q is independent of x. Q doesn't depend, right? Q does not depend on x. So while it is flowing from one end to another end, it remains constant. Not always. Under the condition that we have imagined or assumed one dimensional steady state heat transfer without any internal heat generation. So this point we should make a note of. Right, that equation.